Good day. My name is Gareth Wilkes, and today I'll be providing a detailed summary of the following study entitled An Assessment of the Variation in Limestone Quality Originating from North and South America and Implications for Broiler Nutrition. Before we get started, there are two questions that I would like to propose. The first being, why is limestone important? And the second being, why should we care about analyzing our limestone? The reason why we as nutritionists should care about limestone is because limestone can contribute more than 50% of the total analyzable calcium in a broiler diet. Looking at these four pictures of samples taken from North and South America, we can see not only considerable variation in the particle size, but also the color and presumably geological origin. This variation can lead to subsequent variation in calcium availability, which is rarely taken into consideration when formulating broiler diets, because we still formulate to total calcium. As a part of a worldwide survey looking at fine limestone, the aim of this study was to assess the variation in fine limestone quality originating from North and South America and its implications for broiler nutrition. In terms of the materials and methods of our research, a total of 200 limestone samples weighing approximately 1 kilogram each were collected from various commercial feed mills across North and South America. These samples were transported to the Communique laboratory over a period of 2 years. Upon receiving the samples, each sample was split into 2 aliquots using a riffler. The first aliquot was used to determine the particle size and dynamic solubility, whereas the second aliquot was used for mineral analyses. Particle size was determined using the ASAE 2003 methodology, whereas the dynamic solubility was determined using the newly developed Kim et al. Method, in which we determined the rate of calcium solubility in duplicate at 5 minutes, 15 minutes, and 30 minutes respectively. For the remainder of this presentation, these time points will be referred to as T5, T15, and T30. Lastly, each sample was analyzed for the following 9 minerals using an ICP according to the AOAC 2016 methodology. All data were analyzed using the JUMP statistical package version 15. Raw data was subject to a one-way ANOVA. Where significant differences occurred, means were separated using a student t-test at a significance level of p less than 0.05. Lastly, Pearson correlation coefficients were determined between selected dependent variables. The results of the study have been divided into the following 3 analyses. So if we take a look at our results, firstly comparing the average particle size of limestone from North and South America, we see a significantly larger GMD particle size of samples from North America compared to that of samples from South America. Equally important is the large standard deviation and coefficient of variation of fine limestone analyzed from both continents. If we look at the average as well as the variation in GMD particle size within countries, we see a range of particle sizes ranging from as fine as 30 microns all the way to 900 microns, which highlights the fact that there is no consistency in particle size of fine limestone being fed to broilers across both continents. Looking at the mineral analyses results, we can see that samples from both North and South America exhibit relatively high overall calcium percentage levels of almost 38% respectively. However, if we look closer, we can see that some samples analyzed as low as 30%. This highlights the importance of analyzing the specific limestone used in your feed mill and not just relying on book values. Turning our attention to magnesium, even though there was no statistical difference between the 2 continents, what is important to take note of is the upper reported values for both continents. These values emphasize the fact that we cannot simply analyze limestone for just calcium, as these higher reported values need to be taken into account when formulating broiler diets, as generally speaking, the maximum tolerable magnesium level for limestone is 1%, and values higher than that have been shown to have a laxative effect, resulting in an increased incidence in wet litter. Moving on to iron, we can see that there is significant differences in the reported iron content, with samples from South America exhibiting almost double that of North America. Iron found in limestone is predominantly found in the form of iron oxide, which is biologically unavailable to the bird. Therefore, these higher reported values shouldn't have an effect on broiler production. Lastly, looking at manganese, even though there was no reported statistical difference, what is important to note is the large standard deviation relative to that of the mean for both continents. This emphasizes the fact that large variation exists in reported manganese levels. Manganese plays an important role in bone formation, eggshell quality, and collagen formation. Therefore, this large variation in reported manganese levels can lead to variation in the total manganese consumed by the bird. The commercial implications of such variation need to be studied further. Looking at the correlation between calcium and the other 8 minerals, we can see there is an overall negative correlation. If we use magnesium as an example, we can see a strong negative correlation of negative 0.56, which suggests that samples containing low levels of calcium would contain high levels of magnesium. Similarly, a similar conclusion can be drawn for iron in South American samples. Looking at the dynamic solubility results for both continents, we can see that there is no significant differences in reported mean solubility results across the 3 time points. Both continents exhibited very similar profiles. However, if we look at the next slide, even though there was no significant differences in reported average T5 solubilities across continents, it's clear to see by this box and whisker diagram that significant variation in T5 solubility exists within countries. In order to see if this variation in solubility at T5 is related to the variation seen in particle size earlier on in the presentation, we performed simple regression analyses. The R coefficient of negative 0.59 suggests that the variation in the initial rate of solubility can be explained by particle size. However, as highlighted by the poor adjusted R-squared value, there are lots of exceptions to this rule. These exceptions can be seen in the following correlation graph, by which 2 samples, one from North America and the other from South America, exhibited vastly different particle size rates, yet they both solubilized at the same rate. Furthermore, 2 samples from North America showed similar GMD particle sizes, however, they both solubilized at vastly different rates. This shows that solubility of limestone is not just merely a function of particle size, and that other factors, such as the limestone source and underlying geological rock, play an important role. All this variation leads to an important question, and that is, what is the impact of this observed variation on calcium and phosphorus utilization in broilers? Previous research by Kim et al. Compared the in vivo digestibility of calcium and phosphorus in a corn-soya-based diet using 2 limestones differing in their initial rate of solubility. And what is clear to see from these results is that the faster solubilizing limestone, limestone A, exhibited a significant detrimental effect on both calcium and phosphorus digestibility than compared to the more slowly solubilizing limestone. The potential mechanism by which a more rapidly solubilizing limestone can reduce calcium and phosphorus digestibility is shown in the following animation. When limestone dissolves rapidly, free calcium ions bind to phytate, reducing its availability to both exogenous enzymes and the bird. thereby decreasing calcium and phosphorus digestibility, as well as phytase efficacy, all of which leads to an imbalance in calcium and phosphorus. All this has significant implications for broiler production, since variation in the supply of digestible calcium and phosphorus can impact significantly on the incidence of skeletal abnormalities, production performance, and be of environmental concern. In conclusion, our data has shown that significant variation in the GMD particle size exists within countries. Furthermore, considerable variation exists in the T5 solubilization rate in limestone, which cannot be completely explained by differences in particle size. In terms of the mineral analyses, all limestone had relatively high overall calcium levels. However, there was a strong negative correlation between calcium, magnesium, and iron content. Lastly, I would like to leave you with the following take-home message. We shouldn't only be analyzing limestone for total calcium. Furthermore, particle size is not the only factor that influences in vitro solubility. Other factors, such as the physical structure of the rock, geological origin, and chemical composition, have all been previously shown to affect calcium and phosphorus utilization, as well as phytase efficacy in broilers, and should be considered when selecting a limestone source for inclusion in practical diet formulations. Lastly, a big thank you to Dr. Mauricio Cunha and Dr. Janet Remus from IFF for their continued support and for helping to organize all the samples. A big thank you to the Communique Laboratory team for helping to analyze all the samples, and a big thank you to Dr. Peter Plumstead and Dr. Rosalina Angel for their valuable input and guidance. Thank you. I look forward to receiving any questions.